Initially, there was an infinitely dense mass of matter. This mass underwent an enormous explosion that eventually led to the formation of atoms, molecules, stars, and galaxies, the very structures that we observe in the universe today. For decades, this has been the widely accepted explanation offered by physicists to describe the origin of the cosmos. However, recent research has introduced a new perspective. It suggests that the universe might not have had an origin as early or singular as once believed. Instead, it may be part of a cyclical process in which the universe continuously goes through phases of expansion and contraction, possibly in an infinite loop. Renowned physicist Brian Cox has also expressed doubts about the traditional Big Bang theory. He questions how something can arise out of nothing, a notion that challenges one of the foundational premises of the Big Bang model. His skepticism adds an intriguing dimension to the ongoing scientific discussion. Furthermore, observations from the James Webb Space Telescope have revealed findings that contradict the idea that the Big Bang marked the absolute beginning of the universe. These revelations prompt a fundamental question. If the Big Bang wasn't the true beginning of the cosmos, then what was? Join us on this journey as we explore the origins of the cosmos, challenge long-held assumptions about the Big Bang, and uncover new possibilities at the frontiers of theoretical physics. If you're interested in staying informed about the universe and its mysteries, make sure to subscribe to our channel, like the video, share it to reach others, and turn on the notification bell. Scientists have developed a detailed understanding of the universe's earliest stages through what is known as the Big Bang theory. According to this model, about 13.8 billion years ago, the universe was much smaller, hotter, and denser than it is today. In just a matter of minutes during that time, all the elements that form our world were created. According to the theory, the entire universe, including all the stars and galaxies, was once compressed into a region as small as a peach, with a staggering temperature exceeding a quadrillion degrees. Remarkably, this extraordinary narrative is consistent with all known astronomical observations. Astronomers have analyzed various indicators, such as the remnant electromagnetic radiation from the early universe and the abundance of the lightest elements, and found that their observations align closely with the predictions made by the Big Bang theory. To the best of our current knowledge, this explanation accurately describes the reality of our universe. However, despite its robustness, the Big Bang theory does not present a complete picture. There remains a missing piece, an understanding of the universe's first moments. This challenge arises from the limitations of our current physical theories. While the combination of general relativity and high-energy particle physics provides a solid conceptual framework, the mathematical complexity intensifies significantly as we approach the very beginning of the universe. At this point, our current tools and theories break down and fail to offer meaningful solutions. One major indication of this difficulty is the existence of a singularity, a theoretical point of infinite density at the beginning of the Big Bang. This concept implies that the universe was once compressed into an infinitely small, dense state, which appears physically absurd. To address this conundrum, we must explore new frontiers in physics and develop approaches that surpass the limitations of our existing models. Our current instruments and theoretical frameworks are insufficient for this task. Thus, there is a need for new physics capable of integrating gravity with the other fundamental forces under extremely high energy conditions. This is precisely where string theory enters the picture. String theory aspires to be a comprehensive, physical model that unifies gravity with other fundamental forces, especially at ultra-high energies. In doing so, it offers a potential explanation for the universe's first moments. One of the key concepts arising from string theory is the ekpyrotic universe, a term derived from the Greek word for conflagration or fire. This idea suggests that the Big Bang was not the absolute beginning, but rather a result of a preceding event. It points to a process that is ongoing rather than finite. Extending the concept of the ekpyrotic universe has led to the development of cyclic cosmology, a related theory that has been considered for millennia but now gains mathematical credibility through string theory. Within this framework, the universe perpetually oscillates between massive explosions and gravitational collapses, an infinite series of cycles extending into both the past and the future. Cyclic cosmology was proposed by Nobel Prize-winning physicist Roger Penrose. He was fascinated by a profound mathematical relationship between the early universe, marked by high density, extreme heat and compactness, and the far future state of the universe, which will be cold, greatly expanded, and nearly devoid of matter. Penrose's theory suggests that, at extreme limits, these two vastly different states become mathematically identical. Though it seems paradoxical, the complete absence of matter may in fact be the very condition that enables the emergence of all matter in the universe. According to this view, the Big Bang emerged from what remained after all matter had been consumed by black holes, and those black holes eventually evaporated, leaving behind only scattered photons in a vast void. This nothingness is not absolute. It is still a form of something, a physical yet empty universe. The mystery lies in how this same state can be seen either as a cold, empty universe or a hot, dense one, depending on the perspective. The key to understanding this lies in a mathematical technique known as conformal transformation, a geometric operation that changes an object's size while preserving its shape. Penrose demonstrated that the spatial and temporal structures of the cold, empty state and the hot, dense state can be aligned through such a scale transformation. In extreme physical conditions, the concept of size itself loses relevance. In cyclic cosmology, the sequence of cosmic events unfolds from an old cold state to a young hot state. The hot and dense conditions that characterize the beginning of a cycle are actually the product of the cold and empty conditions at the end of the previous cycle. However, this causal relationship doesn't follow conventional time because, under such extreme conditions, both size and time cease to have their usual meanings. These two states, cold and empty, hot and dense, exist on separate timelines. From the perspective of an observer within one timeline, the cold, empty universe would appear to last indefinitely. In this realm of cyclic concepts, physics and philosophy become deeply intertwined. While cosmology can offer speculative and detailed physical explanations for these cycles, a deeper philosophical question remains. How did these cycles originate? This touches on one of the most profound metaphysical questions. Why is there something rather than nothing? To stay within the scope of physics, there are three possibilities worth considering to explain the origins of these cycles. First, there may be no physical explanation at all. Second, the universe may consist of an infinite series of cycles, where each new cycle is somehow influenced by the conditions of the one before it. Third, the universe might consist of a single repeating cycle, where the beginning of each cycle is caused by some feature of its own end. These possibilities are compelling because they eliminate the need for uncaused events, offering instead a more comprehensive explanation within a physical framework. Within this framework, Penrose proposes an endless sequence of cycles based on his interpretation of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed, at which point it collapses randomly into a single state. Penrose suggests that random quantum events introduce slight variations between cycles. This opens up promising opportunities for experimental physicists, as it may be possible to detect subtle traces or anomalies in the remnant radiation from the Big Bang, clues that could validate or refute aspects of cyclic cosmology. What do you think about these fascinating ideas? Let us know your thoughts in the comments below. If you enjoyed the video, don't forget to hit the like button, subscribe to the channel, and share it so others can explore these profound mysteries of the cosmos.